Hello everyone, in this video we're going to solving a quartic equation, a very special one, so I'm going to present two methods. Let's start with the first method. Now when you look at an equation like this, you're trying to find a solution. Obviously you don't want to use the quartic formula, which is pretty complicated. You can look for a rational solution if you check the divisor of two factors of 2. We're going to end up finding first of all, notice that there are no positive solution because all the coefficients are positive. So you're only going to be looking at -1 and -2, and unfortunately those values do not satisfy the equation. Therefore, we don't really have any rational solution. So we're going to look at it in a different way and to try to factor this. So to be able to factor it, I'm going to represent two methods. Like I said earlier, the first method basically involves some identities that I need to tell you about. So before we start factoring, I'm gonna have you look at the following, and so we're going to factor this expression. First, x to the fourth plus x squared plus 1. Obviously, this equation can be factored by using difference of two squares, add x. First, x to the fourth plus x squared plus 1. Obviously, this equation can be factored by using difference of 2 square and also add x squared and abstract it. And then here you get x up to 4 plus 2x squared plus 1, which is a perfect square, and x squared is of course a perfect square. Now, how do you write the first expression, that is x squared plus 1, quantity squared, and this is of squared? Now, since this expression can be written as a difference of 2 square, it is factorable. Let's go ahead and write into factored from using difference of 2 squares. I can safely say that it's going to be x squared plus 1 plus x, but I like to write it as x squared plus x plus 1. Another factor is going to be x squared minus x plus 1, and you always have to check by using the distributive property. But this is always no identity. This expression comes a lot, so why did I attempt to factor this? Because our expression can be broke down in a special way. That's why I called a special quartic equation. And let's see why it's special. So let's go back to the original x to the fourth plus x 2x squared plus x plus 2 plus. My goal is to solve this equation, but if I can factor it, then solving it would be really a piece of cake. Now notice that this expression can be written as x to the fourth power plus x squared plus 1 plus x squared plus x squared plus x plus. Notice that we broke down the x squared and we broke down the 2 and we got 2 pieces, and then notice that this is piece actually factorable. We just did that one of the factors of that first piece, actually the second piece, so this is going to be factorable by grouping. So let's go ahead and write the factors of this. One first thing that going to be x squared plus 1 multiplied by x squared minus x plus 1 plus, since the second one doesn't really have anything to multiply by, I can use 1x squared times x times 1. Now we have a common factor. Let's go ahead and use that x squared plus x plus 1 is a common factor, so the whole idea is break it down in a factorable way. And now we have x squared plus x plus 1 multiplied by x squared minus x plus 1 plus 1. That is going to give us a plus 2. Here, therefore, we are able to factor this quartic equation into two quadristicated, and since our equation is equal to 0, let's go ahead and set this equal to 0 and look for solution. Finding the solution at the point will be fairly easy. If you use that quadratic formula, I'm just going to give it to you. The solution, or should I say rather a set of solution, would be -1 plus minus the square root of 3 I of 1 over 2. By the way, this is also a very common expression that comes up with a complex numbers. So you know the complex cube root of 1 and so forth. I think we received our video on the 1, 2. Anyways, the other set of solution is going to be 1 plus minus the square root of 71 divided by 2. So what do you notice? All solutions are non-real complex. Great. So this is the final answer for the first method. We're done already for the first method.
So we are already here for the second method. About the second method, obviously the second method is different and it involves, of course, the same idea here. We want to factor this, but how can I factor it without manipulating like in the first method, right? Well, here's what I can do. I can assume that there's going to be two quadratic factors. Well, I can assume that there will be a linear and a cubic factors. That's not possible because we notice that there are no rational solution, so we can't really have a linear factor, at least with integer coefficient, right? Okay, so for example, x plus 1, x minus 1, something like that can never be a factor. So we're going to factor it in such a way that now one thing I want you to know, notice that we don't have x cubed, as this is a reduced quartic, which is assumed the following form. This can be written as x squared plus ax plus 1 times x squared minus ax plus 2. Now the reason why I use a plus ax and minus ax is because when I distribute here and here, I'm going to get the x cubed term cancel out. That's why I'm able to fix my factors. That's why either this method is going to work. Of course, I can at the same time it's -1 and -2 instead of the +1 and +2, because all I need is actually two integers whose product is 2. It can be done in two ways. Now, which of these is going to work? So here's what you're going to notice. If you start well, let's try the -1. So what I'm going to do here, we're going to go ahead and distribute this. Let's go ahead and distribute here. We're going to get y to the fourth. We're going to get the x to the fourth power. And then since the x cube is going to cancel out, I don't really have to worry about it. So I can just go ahead. I mean, if you want, you can distribute it and see that it cancels out like this. And then ax cubed minus a squared x squared minus 2ax, and then minus x squared plus ax plus, you don't have to get 9 terms, so distribute everything over everything, and the x cube cancel out. And if you kind of put it together, like combining like terms, I'm gonna get the x to the fourth minus, notice that the coefficient of x squared is negative a squared. I get negative x negative 2x squared minus 1x squared. That's a negative 3x. So I can kind of write this as a squared plus 3 in parentheses with a negative sign in the front, and then this take care of pretty much all the x squared terms, and these are going to be give me a negative ax, and that's just going to end up with a positive 2. And I have to set this obviously equal to my original expression. And from here, to keep a long story short, 7, you want this to be negative 2, which implies that a squared equals negative. Obviously, that's not going to work because we're looking for a real number, I mean like integer, even like a more specific case, so this option is not going to work. Therefore, we have to go with the other one. Now, the millionaire question is, there a way to find out without trying both? Something to think about. When you set this equal, do you know this expression? We're going to get the following. Let me give it to you, so save some time. Here you go. You can distribute and you know the arrange. If you're going to get that this equal my original expression, which is x to the fourth plus 2x squared, that is equal to 2, meaning a squared equals 1. From here, you will get a equals 1, and that is already satisfied here. Therefore, a equals 1, and we get x squared plus x plus 1 times x squared minus x plus 2 equals 0. And from here we get the exact same solution, and this brings us to the end of this video. Once again, I'm Aaron Madrid. I'm already done discussing my quartic equation for this performance task. Thank you for watching and listening to my video. I hope you guys have a great day.